Hi, everybody. Welcome back to the Feynman Technique. This is going to be a classic Feynman Technique video. I kind of missed doing these videos up in front of the whiteboard, just kind of winging it. I'm not winging it. I have notes. I know basically what I'm going to do. Um, but yeah, I kind of miss doing this. Um, and by the way, guys, I'm going to leave a link to my new channel, Viral Integrals, in the description. If you would please subscribe to that or go check it out. I'm having a lot of trouble getting that one off the ground. This channel seemed to take off much more quickly than that one, but I'm trying to get some of my subscribers from this channel to also subscribe to that one. So please do that if you don't mind. Anyway, so what we're going to be doing today is showing this. Um, by first showing that that integral is equal to that, and that that integral is equal to that value. So we're going to show that this second part right here is true. And by the way, that is the sum of the reciprocals of the odd squares. Well, technically it's twice it. We just divide by 2 and get pi squared over 8, the classic result. Um, but yeah, we're going to show that this is equal to this, and also that that is equal to that, and therefore the sum of the reciprocals of the odd squares is going to be equal to pi squared over 8. All right. So the first thing to show is that that integral is equal to that sum. That's actually the easy part. Give me 1 second here. Pull up my notes. All right, there we go. So, yeah, that's the easy part. Basically, what we want to do is first show that this integral right here is actually, we can actually say that that is twice the integral from 0 to 1 of the same thing. Natural log x over x squared minus 1 dx. Now, I'm not going to show all the steps for that, but basically what you do is this. You take this interval from 0 to infinity and split it at 1 and make two separate integrals and perform the u substitution u is equal to 1 over x on the second one. And combine them, and you will find that this is true. So that integral is just twice the same integral on the interval 0 to 1. All right. And from there, what do we do? Well, we're going to break out geometric series. We're going to say that this is equal to, well, let's see, it's going to be 2. We're still going to have the integral going from 0 to 1. Now, let's see, we'll keep the natural log x because you can't really, well, we could define a series for that. But anyway, natural log x, and then we'll plug in the series representation for our 1 over x squared minus 1. And we have to be careful here because our series actually assumes 1 minus x squared. So we're going to have to add a negative there. So we're going to put a negative outside, and then that becomes x to the 2n. And then we can't forget our dx. All right. Now, from there, it's not very difficult. What you'll do is you'll bring that natural log x inside the sum, switch the sum and integral notations, and then just evaluate the integral. And what you end up with is this, that this is actually equal to that sum. That is actually equal to 2 times the sum. Oh, that's a terrible sum. 2 times sum as n goes from 0 to infinity of 1 over 2n plus 1 squared. All right, so let's take stock. We're showing that that integral is equal to that sum by saying that that integral is equal to twice the same integral on a limited interval, then using geometric series and Fubini's theorem to go from here to here. So we've got the first part checked off. That was the easy part. Showing that the integral from 0 to infinity of natural log x over x squared minus 1 dx without invoking the series is difficult. But we're going to use some Feynman parameterization and we're going to crack it open. All right, so I'm going to erase this now because we're good with that being equal to that. All right. So now we need to show that that integral is equal to that actual value. And what we're going to do is we're going to start with a slightly different integral. We're going to start with the integral from 0 to infinity of natural log of x over x squared plus a squared. Now, why would we do that? Well, what number, when you square it, gives you -1? The imaginary unit. Yeah. So if we can find what that is equal to, and then plug in the imaginary unit I, hopefully we get pi squared over 4. So let's see what happens. Well, first of all, we can't just integrate that. So let's see. Let's factor out an a squared in the denominator. So if we do that, we'll do this carefully. So we still have the integral from 0 to infinity. We have natural log x up top. And we're going to factor out an a squared to get, okay, if we factored out an a squared, we're going to have x squared over a squared plus 1 dx. And of course, this 1 over a squared can come right outside. So we're going to have 1 over a squared. All right, so the next thing to do is just we're going to bring x to ax, which means we bring dx to a dx. All right, I'm not actually doing a u substitution. I'm just bringing x to ax, therefore dx goes to a dx. I hope you're okay with that. Okay. So now what do? We're applying that substitution, so we have the integral. Well, we still have 1 over a squared out front, right? Let's see, x goes to ax, so we're still going from 0 to infinity. Now we have natural log of ax. I'm actually going to write that as natural log of a plus natural log of x. I hope you're okay with that. All right. Over, let's see, if x went to ax, then we'd have a squared, x squared over a squared. So we're just going to have x squared. Oh, look at that. No, that is true. Yeah, that's a plus. I actually thought that I made a mistake with that plus. I thought it was supposed to be a minus because we were minus up there, but it's actually supposed to be a plus. Okay, what was I doing? Yeah, so that's going to be x squared. Yeah, x squared plus 1, and then our dx is a dx. That's going to cancel one of these a's right here. All right. Let's take a look at the second half of this integral right here. Now, you know we can split this using linearity. I'm just going to tell you, this is a classic result, that the integral from 0 to infinity of natural log x over x squared plus 1 dx is actually equal to 0. All right, that can be shown by, again, splitting the interval at 1 and performing the u substitution, u is equal to 1 over x. And then you can see that that integral is equal to the negative of itself and therefore must be 0. But in other words, we're just going to take it for granted that the integral from 0 to infinity of natural log x over x squared plus 1 dx is equal to 0, just to speed things up. So we're just going to erase that part because it evaluates to 0. The addition of that part in the numerator contributes exactly 0. All right. And now you can see that this whole thing is just going to evaluate to natural log of a over a times the integral from 0 to infinity of 1 over x squared plus 1. In other words, we're going to get, let's see, pi on top. We're going to get a 2 on the bottom. We're going to get a natural log a up top, and we're going to get an a on bottom. So look, that integral actually evaluates to that. And now all we have to do is plug in I. So if we plug in I, we get that the imaginary unit is what I mean, by the way, not I. Okay, so if we plug in the imaginary unit into this, we find that the integral from 0 to infinity of natural log x over x squared plus I squared, the imaginary unit squared, which is -1 with respect to x, is equal to that when we plug in the imaginary unit. Let's do it carefully. Pi natural log I. Well, that's the same as natural log of e. We're going to use the principal value to the I pi over 2, right? Natural log I over 2i. All right, well, what's that? Natural log and e cancel. I and I cancel. Pi and pi become pi squared. And 2 and 2 become 4. Pi squared over 4. So we have that integral equals that value, and it's also equal to that sum. So we finally have the result, the value of the sum of the reciprocals of the odd squares being pi squared over 8. So I'm just going to write that down to finish off this problem. We have that the sum, as n goes from 0 to infinity, of 1 over 2n plus 1 all squared is equal to pi squared over 8. And like I said at the beginning of the video, guys, you can actually use this result to derive the other Basel type results, the reciprocal square, the sum of the reciprocals of the odd squares, the sum of the reciprocals of the squares, the sum of the alternating sum of the reciprocals of the odd squares. I'm not sure. You can derive all of them. There's 3 big ones, and they can all be derived from that. Anyway, guys, I hope you enjoyed that. Please subscribe to my new channel, Viral Integrals, and we'll see you next time. There will be a next time. I'll do another one of these videos. It might not be for a while, but we'll see you then.